So thank you very much for this invitation. And it's a pleasure to talk here in this session with Yifang Wang, who's told us about a very exciting perspective for particle physics in the next half century. And also at the other pole, a session with Kevin Costello, who's just told us about a fascinating theoretical insight that's intimately related with a lot of things in string theory. So a lot of people notice that my title is very similar to the title of the last talk, and that's actually because I'll be talking about the work of the last speaker. So when I gave this title and planned to talk about Kevin Costello's work, I didn't realize that Kevin would be talking at this conference. And when I realized that, I thought maybe that meant my talk was extraneous and I should pick another topic. But finally I decided that I think what he's done is really exciting, and I wanted to talk about it anyway, even though it involves some duplication with what you've just heard. So, as I just said, you've just heard about his approach to integrable spin systems, and I'll just be saying a little more about it. So, I start by drawing a space-time picture of elastic scattering of two particles. So, this is in a world of one space and one time dimension. Well, for a moment it could be any dimension. So here we're just elastically scattering two particles. I guess it's 1 plus 1 dimension because I'm not considering the scattering angle. Because of energy and momentum conservation, the outgoing particles go off at the same velocity as the incoming ones, so I've drawn lines with the same slope coming in and going out. There are time delays in scattering, but they would make the picture more complicated, so I've ignored them. But the time delay means that the outgoing particle is parallel to the incoming one, but with a little bit of a delay. Now, in a typical relativistic quantum field theory, there are particle production processes, which are a large part of what makes quantum field theory interesting, and also a large part of what makes quantum field theory rich enough to describe the real world. So here I've drawn a picture of two particles going to 3, and again I'm ignoring time delays, but macroscopically, the outgoing particles are represented by 3 lines in space-time that all come from a common source, to within a microscopic error that depends on the masses of the particles and the ranges of the forces. The symmetries of typical relativistic field theories allow such processes. However, in 2 space-time dimensions, there are integrable field theories that have extra symmetries that move a particle in space by an amount that depends on its velocity. Then particle production is not possible. So here's a process with 2 going to 3, and now I apply a symmetry that moves particles by an amount that depends on velocity. So each line is displaced parallel to itself by an amount that depends on its slope. So now 3 lines that came from a common point are displaced to 3 lines that don't come to a common point. And therefore, after applying a symmetry to the final state and also the initial state, so you take this 2 going to 3 process, which in an ordinary quantum field theory makes sense. In a theory that has a symmetry that moves particles by an amount that depends on their velocity, the picture doesn't make sense, or more exactly, the symmetry can transform it to a picture that doesn't make sense. So in these systems, which are called integrable systems, there's no 2 going to 3, but there still is 2 particles elastic scattering because 2 lines in the plane do generically intersect. Even if I move one by some amount parallel to itself, it'll still intersect the other, and the picture will still make sense. So actually there I've moved both of them by different amounts, but the picture still makes sense. Well, how do we characterize a particle? A particle has a velocity, but in relativistic terms, it's better to speak of the rapidity theta, where the energy and momentum are the mass times cosh theta and sinh theta. And the scattering of 2 particles with rapidities theta 1 and theta 2 depends only on the rapidity difference, theta 1 minus theta 2, which I'll call theta. That's the content of Lorentz invariance for 2 going to 2 scattering, is that the scattering only depends on the rapidity difference. So remember, the slope of a line depends on the rapidity or velocity of the corresponding particle. But the amplitude to scatter 2 particles of rapidities theta 1 and theta 2 is in general not only a function of theta, because there may be different types of particles of the same mass. An obvious reason for that is that the theory might have a symmetry group G, and the particles may be in some representation rho of G. So the picture is then more like this. There's a rapidity difference theta. Particles of type I and J come in. Particles of type K and L go out. You can think of I, J, K, and L as basis vectors for our representation, and we write R, I, J, K, L of theta for the quantum mechanical amplitude that describes this process. Well, R is almost the same as the S matrix, but in discussing integrable systems, an overall phase of the S matrix is unimportant. And the R matrix is just the S matrix with an overall phase not specified. So, but anyway, people working on integrable systems call it the R matrix, not the S matrix. The real fun comes when we consider three particles in the initial and final state. Since we can move them relative to each other, leaving their slopes or rapidities fixed, we can assume there are only pairwise collisions, but there are two ways to do this. There are two generic ways for 3-to-3 scattering to be described as a sequence of three pairwise collisions, namely the pictures on the left and on the right. And in a theory that has symmetries that can move particles by velocity-dependent amounts, these pictures must be equivalent. So, in more detail, the equivalent of these pictures leads to the celebrated Yang-Baxter equation, which, if you write it out with all its indices and all the R matrices, is a horrible-looking mess. So we might abbreviate it like this. But what it says is that this scattering, with particles I, J, and K going to L, M, and O, the intermediate states being Q, R, and S, is equivalent to this one with a different set of intermediate states, U, V, and T. Of course, you sum over the intermediate states on both left and right, and you have to get the same result. So that's a nonlinear relation on the R matrix. So the history of integrable spin systems and also integrable relativistic theories in two space or space-time dimensions, studied by a lot of illustrious people, has given a lot of traditional solutions of the Yang-Baxter equation, which are classified by a Lie group G and a representation rho, with some bells and whistles. First, there are some restrictions on rho and in some cases G. And secondly, there's the curious fact that to me for most of the last 30 years seemed completely crazy, that in many important cases, the model associated to a given group G does not actually have G symmetry. In fact, there are three broad classes of solutions of Yang-Baxter called rational, trigonometric, and elliptic, and only the rational ones have G symmetry. So there's a huge, huge story here, and I really believe Kevin's assertion was correct when he claimed that this perspective should shed a new light on basically all facets of this story. Now, I've motivated my introduction by talking about relativistic scattering, but the same solutions of Yang-Baxter are used for physical models of a completely different sort. The ones most relevant today, which you heard about from Kevin, are integrable lattice models of statistical mechanics, which are constructed directly from a solution of the Yang-Baxter equation. So you draw on the plane a lot of horizontal lines and a lot of vertical lines. In Kevin's talk, they were Wilson operators. And, okay, I've repeated this very busy picture. We label the vertical lines by rapidities and the horizontal lines by rapidities. Here I took all the vertical lines to have the same rapidity theta, but I gave different rapidities to the horizontal lines. And then each segment between two vertices is labeled by a basis vector in the representation. I, J, or K, and so on, with lots of indices in that picture. And a crossing is labeled by the corresponding R matrix. Then you define a model of statistical mechanics where the partition function is computed by summing over all labels, with each set of labels being weighted by the product of the R matrix elements. So this is a model of statistical mechanics with 4 spin interactions, because the basic interaction vertex R relates 4 spins on neighboring lines. So in many cases, you can specialize it to a 2-spin interaction. For example, the Ising model is the most famous integrable lattice model, and a special case of this picture reduces to 2 decoupled Ising models. So basically all the integrable spin systems you know about arise from this construction. That's a synthesis of a lot of wisdom of a lot of people. And these models turn out to be solvable because the transfer matrices commute, which means using the Yang-Baxter equation, the horizontal lines can be moved up and down past each other. So it's a long story to actually compute the partition function, but the starting point is that the transfer matrices commute. Now, perhaps the most obvious question about the Yang-Baxter equation is why solutions of this highly overdetermined equation exist. Well, there's another area in which one finds something a lot like the Yang-Baxter equation. That's the theory of knots in 3 dimensions. So, in knot theory, you usually or often describe knots by projecting them to a plane and then giving some equivalences among such knot projections. Those equivalences are called Witten moves. And here's perhaps the most important Witten move. This picture is equivalent to this one. Now, there's an obvious resemblance to the Yang-Baxter equation, but there are equally important differences. First, in knot theory, one strand passes over or under the other, and that was important in this picture here. In the picture, I specified which one draws above the other by not breaking it. Or let's say here, where you can see better, not breaking it. This one goes underneath. But in Yang-Baxter, the two lines just cross in the plane, and there's no notion of under or over. Also, in knot theory, there's another Witten move that has no analog for Yang-Baxter. So these are two senses in which knot theory is richer than Yang-Baxter. In Yang-Baxter, you don't care about over and under, but in knot theory you do. And in knot theory, you're allowed to compare these two, and that doesn't have an analog for Yang-Baxter. So those are structures present in knot theory and not in Yang-Baxter theory, but there's also an important difference in the opposite direction. In Yang-Baxter theory, the spectral parameter, I called it rapidity so far, but in people specializing in integrable systems refer to the rapidity theta as the spectral parameter. So in Yang-Baxter theory, the spectral parameter is crucial, but it has no analog in knot theory. So there are obvious similarities, very tempting ones, between knot theory and Yang-Baxter theory, but the three differences I just mentioned are equally important. Still, there is an obvious analogy, so let's pursue it a little bit. As I've said, the usual solutions of Yang-Baxter depend on the choice of a group G and a representation rho. There are knot invariants that depend on the same data. The prototype was the Jones polynomial that was discovered by von Jones by now more than 30 years ago. To describe them, at least formally, we work in 3 dimensions, and we let A be a gauge field of G, which is a connection on some G bundle over a 3-manifold or 3-dimensional space-time. So we do 3-dimensional gauge theory, the only difference being that we take the action to be not the usual Yang-Mills action, but the Chern-Simons action. Or more exactly, we usually take the action to be k times the Chern-Simons action, where k is an integer. Now, the important difference of this from standard Yang-Mills theory is that there's no metric tensor needed in defining the action. So since there's no metric tensor, Yang-Mills theory with this action is going to be a topological quantum field theory. We could work on any 3-manifold, but for today, just take the 3-manifold to be R3, and now let K be a knot embedded in R3, like the trefoil knot that I've drawn there. Now we pick a representation rho, and we introduce the Wilson operator, which is just the trace of the holonomy of the gauge field integrated around the knot, with the trace taken in the representation rho. And the usual quantum knot invariants are simply expectation values of the Wilson operator. And you should study the quantum renormalization, but for brevity I'll just say that formally this gives topological invariance because there was no metric tensor involved in the construction. Now, from the knot invariance you make this way, you can't really extract the usual solutions of Yang-Baxter since we're missing the spectral parameter. But it was shown by mathematicians in the 80s, actually, I'm sorry I forget the reference now, that in a sense from these knot invariants, you can extract a special case of the usual Yang-Baxter solutions in which the spectral parameter is taken to I infinity. So that's very tempting, and you'd like to know how to generalize this picture to get real Yang-Baxter theory with the spectral parameter, rather than just Yang-Baxter theory at I infinity. So that's the problem that was stuck for about a quarter century, or I think maybe or at least a quarter century, until the work of Kevin Costello. So how can we modify or generalize Chern-Simons gauge theory to include the spectral parameter? A naive idea is to replace the finite dimensional gauge group G with its loop group, which I'll call LG. I want to stress that this is the naive loop group, not the central extension of the loop group that we meet in conformal field theory, but just the naive loop group, the group of maps of a circle to G, with no central extension. We parameterize the loop by an angle theta. Then the loop group has representations that live at a particular value of theta. So the loop group is just the group of gauge transformations on the circle for a G gauge theory. So if you have a charged particle that lives at theta equals theta 0, it only cares what the gauge transformation is doing at theta 0. So that's the kind of representation of the gauge group that we'll consider, of the loop group that we'll consider. So we hope that this will be the spectral parameter label theta naught carried by a particle in the solution of the Yang-Baxter equation. Now, taking the gauge group to be a loop group means that the gauge field now also depends on theta, and so we could write it like this. But it's important that there's no d theta term, so this is not a full four-dimensional gauge field. The Chern-Simons action can be generalized. We still have a Chern-Simons 3 form, and if we multiply it by the 1 form d theta, we can integrate it over m times S1, where S1 is the loop. This is perfectly gauge invariant. So this is the classical Chern-Simons action of the loop group. And naively, we can use it to study knot invariance for representations that depend on theta, that is, on the spectral parameter. But something goes wrong. What goes wrong is that because there's no d by d theta term in the action, the kinetic energy of the gauge field, as mathematicians would say, it is not elliptic, and therefore the perturbation expansion is not well behaved. So in a standard gauge, the propagator from x theta to x prime theta prime has a delta function in theta, because there was no d by d theta in the action. And because of the delta function, loops won't make sense. Here's a loop with two internal lines propagating from x theta to x prime theta prime, and you're going to get two factors of delta of theta minus theta prime. So you'll get delta of theta minus theta prime times delta of 0. So at that point, you have to go back to the drawing board. What Kevin Costello did was to cure this problem via a very simple deformation. So we take our 3 manifold to be R3. We write x, y, and t for the 3 coordinates of R3. So overall, we now have x, y, t, and also theta, where theta is the loop parameter. Now we combine t and theta into a complex variable, t plus I epsilon theta, where epsilon is a real parameter. So we'll be back in the bad case we just discussed if epsilon is 0, but we want to do the case where epsilon isn't 0. Now, if epsilon isn't 0, we can get rid of it by rescaling t and z. So as soon as epsilon isn't 0, its value doesn't matter, and we can just take epsilon to be 1. But I introduce epsilon to emphasize that the good case arises by an infinitesimal deformation from the naive bad case. So now, in the action, we replace d theta by dz, or dz divided by Planck's constant. And now we regard A as a partial gauge field in R3 times a circle that's missing a dz term rather than missing a d theta term as before. And now the action is the one that Costello described. Now, we've lost the three-dimensional symmetry of standard Chern-Simons theory because of splitting away one of the 3 coordinates of R3 and combining it with theta. We still have two-dimensional topological symmetry. But as we discussed when we were comparing Yang-Baxter theory to knot theory, Yang-Baxter theory does not have three-dimensional symmetry, it only has two-dimensional symmetry. We've lost the symmetry that's missing in integrable systems, and we've in turn gained the spectral parameter. It turns out that if you modify standard term Simon's theory in this way, you get exactly the right properties to get Yang-Baxter rather than knot theory. The three-dimensional diffeomorphism symmetry is reduced to two-dimensional symmetry, but now there's a spectral parameter z that turns out to be the spectral parameter. Sorry, there's a complex variable z that will be the spectral parameter. So our spectral parameters were real in the introductory part of the lecture, but to integrable systems people, they think of it as a complex spectral parameter, and in the rest of the lecture, our spectral parameter is the complex variable z. So as I've presented it so far, space-time is R2 times R times a circle, which is C star, parameterized by z, with the complex one form dz in the action. As Kevin mentioned, the action makes sense in a more general situation involving a topological two-manifold sigma and a complex Riemann surface C with a holomorphic one form. But it turns out that to make the quantum theory work, you want omega to have no zeros. Intuitively, the theory doesn't work there because it corresponds to h bar being infinite. And so it ends up that there are three cases of complex Riemann surfaces that work, and they correspond to the three traditional classes of solutions of the Yang-Baxter equation: rational, trigonometric, and elliptic. Now, the first point which Costello kind of explained in his talk is that the theory has a sensible propagator and a sensible perturbation expansion. The basic reason for a sensible propagator is that although d by dt that we had in the naive theory is not elliptic, we've now replaced it by d by dz bar, which is a good operator with a nice inverse. So after a suitable gauge fixing, the propagator is basically what Costello wrote. Here's a slightly different version of it. And that's the propagator for the case that the topological space is R2 and that the complex space is just the complex z-plane with this measure. So to get a propagator requires gauge fixing. Well, the gauge fixing was done in a natural way that used this metric and gave that answer. So then with this propagator, one of Costello's main results is that the perturbation expansion is well defined. That's a tricky point because this theory is actually unrenormalizable by power counting. So on that basis, one would not expect a well-defined well-behaved quantum theory. But the theory also has no possible counterterms because all local gauge invariant operators vanish by the classical equations of motion. So I'm not sure what most of you would have said about a theory unrenormalizable by power counting but lacking counterterms. But anyway, Costello uses a fairly elaborate algebraic machinery to prove that the theory has a well-defined perturbation expansion. Now we consider Wilson operators, which are holonomby operators, where to begin with, L is a loop in the topological space sigma times the complex space C. But we only have a partial gauge field that's missing a dz component. So we would not know how to do parallel transport in the z direction. And since we can't do parallel transport in the z direction, as Costello explained, our Wilson operators have to live at a constant value of z. So L has to be a loop that lies in the topological space at a particular value of z. Now let's consider some lines that meet in the topological space in the familiar configuration associated to Yang-Baxter. So the lines now are labeled by values of z, which are constant for each line, for the reason I just explained. But still we can draw two different pictures. Well, two-dimensional diffeomorphism invariance means we're free to move the lines around as long as we don't change the topology of the configuration. So I can move this middle line to the left or right, except that I should worry what happens when it crosses this point. So the only thing might happen, so the answer will be constant by two-dimensional symmetry if this line is to the left of the crossing point, or if it's to the right of the crossing point. But we should worry whether there could be a discontinuity when the middle line crosses the crossing point of the left and right lines. but assuming Z1, Z2, and Z3 are all distinct, the well-definedness of the perturbation expansion ensures that there is no discontinuity when the middle line is moved from the left to the right, because there's actually no singularity in the full four-dimensional picture, since the three lines are not intersecting in 4 dimensions. There are different values of Z. So the propagator was nice enough to make it clear that there's no discontinuity when we move the middle line from left to right. Topological symmetry says that it's constant on the left, constant on the right, and the smooth propagator says there can be no discontinuity in the middle. So that's why the two pictures are equivalent. So two configurations that differ by what we might call a Yang-Baxter move are equivalent. And likewise, in the configuration associated to integrable lattice spin systems, we can move the horizontal lines up and down at will. But why is there as elementary a picture as in the lattice spin systems, where you can evaluate the path integral by labeling each line by a basis vector and each crossing by a local factor? Why is everything as elementary as that? Well, this is a little tricky and depends on picking the right boundary condition, but there's a way to make it work for each of the three classes of model. Simplest to explain is the rational case in which the complex manifold is just the complex plane. So here the boundary condition we need is just that the gauge field is 0 at infinity in the C direction, and that in quantizing we only divide by gauge transformations that are 1 at infinity. Then we find that the classical solution where A is 0 is unique. It has no deformations up to gauge symmetry and also no unbroken gauge symmetries. So when we expand around the trivial solution where A is 0, perturbation theory is unique. Perturbation theory is straightforward conceptually. There are no unbroken gauge symmetries to worry about and no moduli to integrate over. So we just draw Feynman diagrams. And the reason we're going to get a simple answer is the same as the reason you might have worried about whether the theory existed. The theory is infrared trivial, so it's going to give a simple answer. Infrared trivial is the flip side of the fact that it's unrenormalizable by power counting. So effects at long distances in the topological space are negligible. I put the phrase long distances in quotes because two-dimensional diffeomorphism invariance means there is no notion of distance on the topological space sigma, the first factor of sigma times c. A metric only entered when we fix the gauge. Remember, we used the metric dx squared plus dy squared plus dz squared. We could just as well take a very large real b and take e to the b times dx squared plus dy squared. That means when you look at this picture, you can consider the vertical lines and also the horizontal lines to be very far apart compared to the differences between the z's. In such a situation in an infrared free theory, effects that involve a gauge boson exchange between two lines that don't intersect are negligible. So it's like exchanging a graviton between distant galaxies. That is not going to have much influence on atomic physics in the two galaxies, because gravity is infrared trivial. Now, you could worry about gauge boson exchange from one line to itself, because you have to integrate over A and B, so they don't have to be far apart. But there's nothing that gauge boson exchange from one line to itself can really do. Such effects correspond roughly to mass renormalization in standard quantum field theory, and in the present situation for straight Wilson lines, there's really no interesting effect analogous to mass renormalization that's conceivable. When two lines cross, we get an integral over A and B, and the integral converges. So infrared triviality means that if A and B are large, the propagator is small and the integral converges. So the integral converges, and it receives its significant contributions only when A and B are not much bigger than Z minus Z prime. I'll say what it converges to in a moment. So now let's look at a general configuration like the one related to the integrable lattice models. We can draw very complicated Feynman diagrams, but the complications are all localized near one crossing point or another. So we can draw a mass near any crossing point we want, but a contribution relating one line to another is negligible, and any contribution that isn't near one of the crossings is irrelevant. So away from the crossing points, since the gauge field was 0, that was the unique classical solution we're expanding around, each spin is just interacting with A equals 0, so it just behaves as a free spin. And there are interactions, but only when they cross. So now, summing up these diagrams, we get the recipe of the integrable lattice model, where we have to sum over the state of the spin when it's propagating freely, and when two spins cross, we have to sum up all the effects of gluons at those crossings. So this makes it clear that in the presence of the configuration of Wilson operators that Costello introduced, the path integral can be evaluated by the standard rules discovered by people who work on integrable spin systems. But why is the R matrix obtained this way the standard rational solution of Yang-Baxter, or one of the other standard solutions if we did one of those cases? Well, Kevin already told you the answer in his talk, but I'll just very briefly state it. In his paper, he explicitly evaluates the lowest order correction that the R matrix is 1 plus H bar times something. The something is usually called little r. By explicitly evaluating this diagram, it's a nice and pretty calculation that he almost did for you in his talk, and you get the standard answer that you can find in all the integrable systems papers. And then, once the first order deformation is known, general algebraic arguments about the Yang-Baxter equation imply that the whole solution is uniquely determined by the leading correction. So I have one last comment. So Costello's theorem is about perturbation theory. He proved that to all orders of perturbation theory, the path integral for his configuration of Wilson lines agrees with the perturbation theory of the integrable spin system. But his theorem shows that actually, in this particular theory, and unlike most quantum field theories, perturbation theory converges. As a physicist, one would like to give an a priori non-perturbative definition of the theory, which would have the claimed perturbative expansion. To do this, it appears one has to go to string theory and use a certain brane system, the D4-NS5 system. That step would involve ideas somewhat similar to the ones that I used in relating the Jones polynomial to the D3-NS5 system. Thank you. Well, I can't completely comment on the string theory construction, but I will just comment on the part of your question that asked, what's the 5-dimensional analog of the story I explained in this talk, and that Kevin talked about in his talk. So it actually has to do with Costello's last paper, which I haven't understood very well, but it's on a 5D analog of Chern-Simons theory, where he considers a space that has one real dimension and two complex dimensions, and there's now a partial connection that has a T component and Z bar and W bar components. And the action is dz dw times the Chern-Simons 3 form. And there's a story which I'm sure is at least as fascinating as this one. I wouldn't at present be competent to explain it. So I think I can't do more now than to advertise the paper.
But this 6D also the same.
You can go to 6D. Well, 6D gives you homomorphic Chern-Simons, which is known to be relevant to string theory because, for example, it's related to the space-time superpotentials observed in certain compactifications. I doubt that it has a relation to integrable systems, although life is full of surprises. I was rather surprised that the 5-dimensional one is related to integrable systems. Yes.
Is there similar things in the D4 and S5 system?
So the question, there's an analog of there's a different generalization of Chern-Simons theory, which is Kovenov homology, which also has, well, it has a variety of string theory realizations, with the first version studied by Gukov, Hoffa, and Schwartz. It would be interesting to address this question to Kevin. In fact, he's here, so let's ask. I assume you're here, Kevin, somewhere. I don't know. I don't know if there's, okay, I don't know whether there's room to combine everything. So Kovenov homology can be described by a D4 NS5 system. And this can also be described by a D4 NS5 system. But you have to do different things with them, and I'm not sure they're compatible. But there's always the D5 NS5 system, so hope springs eternal. Let me not say no.
Yes.
Is framing intentionally play any role here? Does the framing effect in pure consensus theory?
Are you asking about the framing anomaly? So, yes, I hit it, and Costello kind of did also, I think. So, there is a framing anomaly that's more complicated than the one in usual Chern-Simons theory. And if you take the topological space to be a plane, there's no framing anomaly if the lines are straight lines. So, okay, the usual integrable system arises, as Costello explains, the topological space is a torus, and the Wilson lines are circles, which you can think of as geodesics on the torus. And with nice geodesics, you don't really meet the framing anomaly. But there's something which I initially found rather surprising. But if you consider anything other than geodesics, you run into a framing anomaly. And I don't fully understand it. I mean, I know how to calculate it. And in a more abstract algebraic way, I think it's, in a more abstract way, it's known in the integrable systems literature. So classically, a Wilson line has a definite value of z. I'll just tell you what the framing anomaly says. Classically, a Wilson operator has a definite value of z, but quantum mechanically, that's true if the line is a geodesic. But if it bends, then z has to change along the Wilson line in a way that depends on the acceleration.
Okay, thanks.
By the way, I answered you only for the framing anomaly for Wilson lines. There is a story about the framing anomaly for the two manifold. I think I'll defer on it to Costello, though.
No further questions. Is there a question?
I can't quite hear the question. Sorry, speak up. The question's about the theta angle in gauge theory? No? Well, the usual theta angle in super-Yang-Mills theory is built into this, in the sense that adding a constant to z is equivalent to shifting theta by a constant. So the usual theta angle of super-Yang-Mills doesn't give anything new, at least if you consider precisely the setup in my lecture. There might be other interesting things to do. I'm not certain if I understood the question, so you can ask a follow-up if I misunderstood.
Okay, I think let's thank the speaker again.